Welcome to Lecture 6A, entitled Directional Derivatives and Gradient. This lecture consists of two components. The first one basically makes heavy use of the material in Reading Assignment 1 up to including Section 2, and in part Section 15.5 of the text. Lecture 6B will have some examples, but also takes a more conventional approach in terms of explaining directional derivatives and the gradient within the textbook itself. So the objectives of this lecture are to develop the tools for determining the slope on a surface in a given direction and the direction in which the slope takes on a maximum, minimum, or zero value. And the concepts and definitions that we'll basically develop over the course of this lecture are the directional derivative, which is nothing more than a scalar representing the slope in a particular direction, and the gradient, which is a vector representing the direction in which the maximum slope is attained, and the magnitude of the vector is the maximum slope. All right, as usual, this second slide is an outline slide indicating the contents of this presentation. I'll just move on to the next slide. All right, so for point of view of motivation, let's look at a particular example in terms of where the calculation of slopes might be of interest. And that would be, for instance, to compute the slope that a mountain hiker sees going up or down or sideways on a mountain. So that's basically the problem statement. What we'd like to do is determine what the slopes are as the hiker moves up and down the mountainside. So the question is, how do you compute the slope as a function of position? In other words, where you are and the path that you're taking. So the key points and steps taken to solve this problem. Step one is to define a position vector that follows the path of the hiker. So that means it'll have three components, the vector. Step two is determine the projection of the vector tangent to the direction of motion on the surface onto the xy plane. Right, so that basically is the vector with the z component removed. That's the tangent vector. And the third step is to convert the tangent vector projected onto the xy plane into a unit vector. We basically are interested only in the direction and not the magnitude, and so a unit vector is a suitable choice in terms of determining direction. All right, so we'll start with a simple illustration, and this is available in terms of a simulation. You've got a slider here, which is t. And what t will do is basically trace a position vector, which would start over here and gradually work its way until it reaches this corner here. And there are two vectors here, position vectors. One is to the surface, which is one in blue, and the one in red, which is the projection of the position vector to the surface onto the xy plane. So this is basically the picture we're dealing with. This is just a cross-sectional cut so you can see the contour of this mountainside. All right, so we want to basically determine what the position vector is. So we're going to have basically the position vector to the surface and the projection on the xy plane. Now, the actual development of a position vector can be done in two different ways. One is you can do a parameterized representation of the position vector in 3D, or an explicit representation of the vector in 3D. In a parameterized representation of vector in 3D, the x, y, and z components basically are all functions of some variable t. Now, because there's a surface, that means z is a function of x and y, but x and y's are functions of t. So effectively, there's only one variable basically defining the position that the hiker takes in walking up and down a mountainside. In terms of explicit representation, we basically know or given information about what y is a function of x. All right? And so that's an explicit representation. So in this case, the position vector would have an x component, which is x. The y component is a function of x, which will be a given. And the z component will be a function of x and y, but y will be a function of x. If we then look at the projection onto the xy plane, which ends up being a 2D vector, then all we're doing basically is removing the z component and just rewriting the vector with only two components. So as again, just a reminder, position vectors, right, which trace out a contour, are function of only a single variable. In the case of parameterized representation, the variable t in this case, an explicit representation x. All right, so that's another note here, and that is, okay, how do you make a decision as to whether or not you do a parameterized representation of the position vector or an explicit representation of the position vector? It's actually going to be a choice, a matter of choice, but there are certain rules of thumb which will be helpful. So for example, the position vector for closed curves is easier to handle using a parameterized representation, since the complete curve can be represented by a single function. For the explicit case, the position vector for the top and bottom part of a closed curve are represented by two different functions. For example, a circle of radius 1 would have to be represented by two semicircles. That is, y equals square root of 1 minus x squared, which will be the top portion, and y equals minus square root 1 minus x squared, which is the bottom portion. And x would vary between minus 1 and positive 1. All right, so we just quickly again review the relationship between position vector and tangent vector. This comes up so often in this course, it's certainly helpful to constantly review it, just so the main message gets across. So you'll notice here, for instance, we have some form of contour in 3D. We have a position vector evaluated at t, some variable t, and then we basically look at the position vector a little bit later, a different value of t at t plus delta t, which is this blue line that you see here. And the difference between those two vectors is this red vector here. This is the delta r that you see here. Now you can basically look at this on an expanded scale where you trace out this with smaller increments. So there's a blue and another position vector. And in the limit, basically this gets increasingly closer and closer to the first one. And so we expect that this basically will start to look something like a derivative. And this is essentially what's outlined here. So this tangent vector, which is the process of taking the limit of delta r, how do we obtain it? Well, delta r is just rt plus delta t minus rt. But just by a trick, we divide through by delta t and multiply by delta t. And notice that this here, this becomes delta r over delta t. But in the limit, delta r over delta t is just the derivative of r with respect to t, and delta t just becomes dt. So this limiting process then basically allows us to compute the differential arc length, sometimes written as ds, sometimes written as dr. Okay, this is a vector, and so that would be what the vector looks like right at that point right there, but tangent to the contour. It can be written either in this form, or in this form, or this form. It's just different conventions are used. So for instance, if you look here, the form that's being used is this form here. Okay, so this is the ds. This is just the r prime vector, whereas this is the actual arc length vector. All right, so let's look at the position and tangent vectors of the path projected on the xy plane. So this one we've already just looked at. So on the xy plane, that's a vector, position vector is xy, between a lower and upper limit of t. And on position vector for the explicit representation would be x, but the second component would be a function of x, so y be a function of x. The vector tangent to the projected path in the xy plane for parameterized representation, where we just take the derivative with respect to t, and this just becomes x dot t, y dot t. Again, here are the expressions for x dot t and y dot t. And for the explicit representation, we're taking the derivative with respect to x, in which case this becomes 1. Our derivative of x is 1, y dot x being dy dx. We're interested in the unit vector in the xy plane. So what we do is we take the rx, this vector here, and we divide by its norm. So we do it for the parameterized representation case and the explicit representation case. So here is the unit vector, which has an x component and a y component. And so the magnitude of this would be just x dot squared plus y dot squared square root. And so here's the unit vector. Similarly here, we'd be using instead the expression for rxy, which is here, and its magnitude would just be 1 plus y dot x squared square root. So this is the unit vector. The last thing we're looking at is the differential length of a path on the xy plane, and that would be dsxy is the magnitude of r dot xy dt. The dt comes in because we're interested now in the arc length, and this just becomes x dot d squared plus y dot t squared dt. Similarly, in the case of explicit representation, this just becomes a dx, and this becomes dy dx squared. All right, so let's take a little more detailed look at what's going on. Let's consider that the hiker is at a position on the hill and now has an option of walking in different directions. And so that's what this picture shows. So for example, here on the XY plane, this red arrow represents the direction in which you want to walk. And this circle represents just the radius. And we're going to let this radius get smaller and smaller, vanishingly small, so that we only see what's happening in the neighborhood of the point in the XY plane. If we now take the value of x and y on this circle and compute its equivalent z value, then basically what we're seeing is this circle here, which has been essentially what is happening on the surface. And again, we let this collapse to 0. So effectively, we're looking at just the tangent to the surface here. So h basically here, this slider allows you to control the radius of this circle. And t basically allows you to control the positioning of this vector, right, going around. The black line is basically the path taken on the xy plane. And the blue is the actual direction that the hiker takes when walking on the mountain surface. So this is just an explanation of this diagram here. Okay, so we want the differential vector tangent to the curve on the surface. And so the parameterized representation of the vector tangent to the path on the surface, we take the derivative with respect to the parameterization variable t. This is the position vector. We had x, y, and z, which was a function of x and y. But we want derivative with respect to t. So on this term here, we're going to have to apply the chain rule. So the chain rule would be dz dx, dx dt, plus dzy dy dt. And again, x dot t is dx dt, y dot is dy dt. If we're interested in the arc length, then effectively we're just looking at the arc length vector, and it was just multiplying through by dt. In that case, the expressions are identical, the only difference being that it's multiplied by dt. All right, so the next thing we do is we're going to apply another trick. So if you look at this term here, all right, it's a scalar, but it's a sum of two components. But we could also look at this as two vectors that have been basically, you apply a dot product to. So if we take this and pair them, and take this and pair them, and each paired quantity is a vector, then we end up with this vector and this vector. If we take their dot product, we end up basically with the original expression. But this is useful because we end up now with this new vector, this vector we don't understand, and we're going to actually give it a physical name. And this x dot t y dt is the tangent vector. Okay, x dot t y dot is done in the xy plane. So these values that you see here, so this, and all of this are represented by the x component of the differential arc length, the y component, and the z component. If we do an explicit representation of the vector tangent to the path on the surface, then the only thing is everything is now a function of x. So the tangent vector on the surface is just dr dx. In this case, we would have 1 dy dx, and then using the chain rule in this case, we're going to have dz dx, dx dx, which means 1, plus dzy dy dx, which is the term that you see here. In this case, x varies between x subscript a and x subscript b. It's an upper limit and lower limit. Okay, so the next thing let's do is basically to look at the arc length, a differential arc length vector, again, based on an explicit representation. So the difference only is that this just has a dx now. Okay, so this looks the same as this except the dx. And again, we play the same trick as previously. We realize that this can be expressed as the dot product between two different vectors, this one here and this one here. And so that's the x component of ds, this is the y component of ds, and all of this is the z component of ds. So that basically gives us what we need, and so now the next step is actually to get to our end goal, and that is what is a directional derivative and also the definition of a gradient. Okay, so the definition of the directional derivative is the slope of a curve at a given point on the surface in the direction of the projected curve traversal in the xy plane. So looking at the previous slide, this is the directional drift. It's a slope. So this slope is evaluated at some point on the surface. The denominator basically is the direction in the xy plane along the direction of traversal. This is a differential length. And this is the change in height that you see basically going along that path. So the ratio of those two is the slope at a given point on the surface in a given direction. Okay? And it's evaluated at a point AB. So that's the definition. So now let's go and substitute in here for the two cases, the parameterized representation and explicit representation, and see what we get. So from the previous slide, dsz was this. That was the z component. And dsxy, basically, this was the dsxy component. So if we take these, the next thing to do is to essentially take all of this and put it underneath x dot and y dot. And so I've just shifted these underneath as in this form. We have the vector here, and we have this vector here. This, by the way, now becomes the unit vector. So if you were to take the magnitude of this, you'll end up with 1. So this is u subscript x, this is u subscript y. Explicit representation, the only difference would be basically what this looks like and what this looks like. So here you'll see 1 dy dx, and 1 plus dy dx squared. By the way, you notice dx is canceled here, and the dt's cancel here. In this case, we end up with, again, this put it under here, this put under here, and we end up with this vector here. But this is a unit vector. You can show that for yourself. And so this just becomes u subscript x, u subscript y. Notice that doesn't matter which way you go, parameterized or explicit representation, we end up with the same answer. Okay, so now basically we come up with a mathematical expression for a gradient and directional derivative. We're going to define this vector as a gradient vector. Okay, so this symbol essentially says we're doing an operation on a scalar function, and that operation is of this form. And what it does, it takes a scalar function and produces a vector, and the components of the vector are based on doing this calculation. Okay, so that's basically a new type of operation that we're performing using this gradient operator. All right, and the directional derivative will just be basically copied over, but now with this defined by the gradient vector, this becomes the gradient vector dot unit vector. uxy basically now is described as the unit vector. Now we can also write a dot product in another way. We can say it's the magnitude of this vector, the magnitude of this vector, and the cosine of the angle between the two. So we end up with this. But the unit vector has magnitude 1, so we end up with the magnitude of the gradient of phi and cosine phi. Phi is the angle between the gradient vector and the unit vector. Unit vector would be the direction in which you want to go, and the gradient vector is a specific vector that's pointing in a direction at which you would be getting the maximum possible slope, right? And if you look at this, cosine phi, if phi is equal to 0, that means the direction in which you're pointing is exactly in the same direction as a unit vector for the gradient vector, which means you're pointing in a direction in which you observe the maximum slope. And what is that maximum slope? It's just the magnitude of that gradient vector. All right, so this is how you basically interpret a directional derivative and also the meaning of the gradient vector. So that more or less concludes this lecture. Thank you for listening.